So we're going to focus on a special type of chemical equilibrium in which you're dealing with a salt that is generally what we call insoluble. So when we talk about how soluble is a salt, we could say that it's highly soluble, we could say that it's mostly soluble or soluble, moderately soluble, sparingly soluble, and insoluble. So kind of listed from the top bottom means that it will go into solution at the top, and at the bottom we say it doesn't go into solution. With that said, we're going to focus on basically a type of chemistry problem that's important, dealing with insoluble salts. Okay. Now, was it last night? Yeah, I was getting ready for today, and I was like, I asked my husband, I'm like, now how are they supposed to remember these solubility rules? And I'm like, there's not that many of them. These are called solubility rules. So most salts where the cation is sodium, potassium, lithium, or ammonium, are soluble. Just remember it. Like, how are they supposed to just memorize it? Most salts where the anion is nitrate, hydrogen carbonate, what is that? Perchlorate, chlorate, and this is acetate. Those are soluble. Most. You hate the whole most thing. These are rules. Most salts where the anion is the chloride ion, the bromide ion, the iodide ion are all soluble. Now we get to some exceptions. In Le Chatelet's experiment, the Chatelet's principle lab we did, do you remember where the last one where you had silver chloride precipitate out? An exception is where silver combines with these things. So silver chloride, silver bromide, silver iodide precipitates out. Inside. So that's how that works. So don't blame me, it's like there are exceptions. SO42- is sulfate, so most salts of sulfate are soluble. Exceptions is with the cation is calcium, strontium, barium, silver, the mercury 1 polyatomic cation, or lead 2. Okay. Salts of these anions are generally insoluble, so they won't go into solution. Carbonate, phosphate, this is the oxalate, chromate, sulfide, hydroxide, or oxide. Unless, so they're insoluble unless your cation is ammonium, sodium, potassium, or lithium. This is the way that a little more concisely maybe than the few slides I showed you, the way that OpenStax handles it. Soluble compounds contain, exceptions to this rule, and then insoluble compounds contain, and these are exceptions to that rule. So one way or the other, you're going to want to try to get these under your belt. Now, some of this, actually, I told you we're going to be dealing with insoluble salts kind of for the rest of this part. Some of these rules will kind of be reinforced by the salts that we'll pick. So we're focusing on insoluble salts. Like if they're insoluble, then why look at them? Because they don't dissolve. The problem is they dissolve just a little bit. Okay, they're what we say in chemical equilibrium. So here we have an ionic compound and submerged in water, and the dissolving process would look like this, where you have kind of, these are kind of like, is this right? Waters of solvation, S-O-L-V-A-T-I-O-N, kind of carrying off the ions from the crystalline lattice structure. Now it's an equilibrium, it's dynamic, so that actually some of these cation and anion might find their way back to the crystalline lattice structure and new ones kick off. So at equilibrium, you have just the right amount according to the equilibrium constant expression of your cation and anion floating around in there. So we could take this and make it into an equilibrium expression. Looks like this. Equilibrium expression from left to right. On the left, we have our solid salt that we're trying to dissolve. On the right, in the product, we have now, so the subscript of the cation would be how many cations you get. So it makes the coefficient on the product side, right? And I don't know if you remember kind of the crisscross thing, but the charge of the cation will have the magnitude of the number of anions you have. Can you remember that, kind of crisscross? That's kind of what you're seeing here. So you have X particles of A, probably raised to the Y plus, and you'll have Y particles of B raised to the X minus. Well, we know what we can do with chemical equilibrium. We can write a chemical equilibrium, we can write an equilibrium expression, equilibrium constant expression, and it looks like this. So the solids don't appear, right? Waters don't appear since it's aqueous. I don't have water here. But all that's going to appear is the products over the reactants. There are no reactants. So we simply have the products raised to their stoichiometric coefficients. Basically, at what we learned before. Molar concentration of cation raised to the X power because they're X particles. Molar concentration of anion raised to the Y particles. So I kind of warned you that this is going to happen. Actually, in Unit 4, we're going to have a few other equilibrium constants. So this is a special equilibrium constant just for insoluble salts called KSP. Goodness, we've talked about a KC, a KP, right? This is the KSP. SP stands for solubility product, and I think it's coming up. SP stands for solubility product. So KSP is a solubility product constant. You know that you're dealing with an insoluble salt. You have a feel for what that equilibrium constant expression will look like, hopefully. Okay. So we've talked earlier, like usually like how many grams of a salt would dissolve in 100 milliliters of water. That's the solubility. And it is related to the KSP. It is related to the solubility product constant. They're related, but they're not. They're different. They're like both cats, but they're different species. Okay? Solubility is what we've dealt with before. Solubility is the maximum amount of salt that you can dissolve in an amount of water or an amount of solution. Like I said, a lot of times our solubility is given in grams of salt per 100 milliliters of water. So let's go ahead and jump in there and see what this looks like. So silver chloride, in Le Chatelier's principle, you did some things to try to make it precipitate. Okay, so silver chloride, generally insoluble salt. It's in equilibrium, and I like to kind of think of, I do, and maybe, I don't know if I do them on I do a lot with sludge. So to me, this could be a test tube. I'm going to make it a beaker, but you guys actually probably, I don't know if you saw it kind of fall down, but you actually saw flakes of AgClS. Okay, so I know that when I see that this is what I have going on. I have silver chloride in its solid state, and it's in equilibrium with a saturated solution of Ag plus, Aq, plus Cl minus Aq. And I would write the equilibrium constant expression like this. Equilibrium constant expression. It's the products over reactants raised their stoichiometric coefficients. Of course, since the reactant is a solid, it doesn't appear, and we put SP with our K there. Now, if things get a little interesting when you have more than one cation or anion that's formed on the product side. So, for instance, Ag3PO4, silver phosphate, make sure, this will catch a lot of us, make sure that we recognize that we're going to have 3 Ags pluses and 1 PO4. So now when we write the K, I call this the KSP expression, the equilibrium constant expression. Our KSP will be equal to the molar concentration of your Ag raised to the 3rd power times the molar concentration of phosphate raised to the 1st power. I'm a firm believer, and sometimes on your tests I will make you write this. I'm a firm believer when dealing with precipitation equilibrium, like what this is, to write the balanced equilibrium first, and then write the KSP expression after that. Okay, so here we have 2 clear solutions. This is silver nitrate, and then we have sodium iodide. Now, one of the types of chemical reactions that can happen is called an exchange reaction, chemical exchange reaction. where the cation, the silver is going to go, this cation is going to go with this anion, so we're going to get silver iodide, and then this cation, Na, is going to go with the NO3, so we're going to get sodium nitrate. It's an exchange reaction. So the thing is either one of those salts insoluble? Is either silver iodide insoluble or sodium nitrate insoluble? Then you're going to see a precipitate form. And yes, actually down here, if you look up the solubility rules that I covered, you're going to see that, I can't remember what it would be. Oh yeah, most halogens, like the iodides, the chlorides, the bromides, most of them are soluble. I said unless they're with certain cations, and silver is one of them. So after the exchange reaction, if something's insoluble, you'll see that cool, sometimes it's milky white, sometimes it's fluffy, but if it looks not clear, that's a precipitate. So there you go.
Could you go back to the previous slide? I just have a quick question.
Mm-hmm.
Why isn't there a 4 in front of the PO or in front of the phosphate on the
Here?
side?
Okay, that's a good question. The way this works is phosphate is a polyatomic anion. So I only have, so this will stick together, and I could put parentheses around this and put a 1 there. I only have one of those.
Oh, because it's, okay, yeah.
It sticks
and then
together.
It's 3 plus.
Mm-hmm.
Okay.
Yep.
Or 3 minus.
Yep. Sounds like you got it.
So it's like that for any of them that have that number at the end. Regular.
If it's a polyatomic ion, so this is where you might want to go back and brush up on your Chem 1 stuff, like nitrate, the NO3 minus 1, and so
those all match together and they don't count as that little, okay.
They all match together and they wouldn't be pulled out. Think of it this way, when your salt breaks apart or ionizes, okay, picture what it's going to make. So your PO4 is going to stick together, phosphate. And it wouldn't hurt to remember that phosphate actually is a -3 charge. So that actually could help you. Couldn't hurt. You're welcome. So one of the things we talked about with equilibrium constants, not necessarily equilibrium constant KSPs, we said that the smaller they are, does it favor the reactant or the product side? It's pretty small. If it's small. The products are on the top, so if it's small, it means you don't have much on the top, but you have a lot on the bottom. There's no denominator. So actually, a small Kc favors the reactant side. Small Kc favors the reactant side, yeah? And the reactant side in these equilibria is the salt in its solid state. So to me, I kind of think through that, and the way this works then is that the smaller the KSP, the less soluble in general it is. The smaller the KSP, the less soluble in general it is. I'm going to kind of have to backtrack a minute in a little bit, kind of relating KSPs with solubility, but oh, goodness. So this is from a different textbook, and notice that the temperature has to be given, standard temperature 25 degrees Celsius. So these are all KSPs, and we could, I'm not going to, but for each one of these, we could write a KSP expression. So let's, kind of like what we were talking about, blah, 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 blah. Oh yeah, well here's a good one. See, magnesium phosphate. To get the neutral formula for magnesium phosphate, you'll need 3 Mg+2s, and you'll need 2 PO4 3 minuses. So then notice that the balanced equilibrium has 3 Mg+2 and 2 PO4 3 minuses. So, and we could write the KSP expression, that would be what? The molar concentration of molar concentration of Mg+2 cubed times the molar concentration of PO4 3 minus squared is equal to 1 times 10 to the -25th. So this is the sort of problem you might run into. In this case, we're given the solubility. Actually, this is what we call the molar solubility because it's moles per liter. The molar solubility of lead 2 chloride, and we're supposed to come up with the KSP. If I don't ask you on the test, it doesn't hurt to write the equilibrium of lead 2 chloride. Lead 2 chloride solid to what? Okay, write the cations on the other side. If I don't ask you, you probably should. So, the balanced equilibrium of dissolving lead 2 chloride looks like this. And then we could write the KSP expression from that. I'd look at it stepwise. So the KSP expression is going to be the products raised to stoichiometric coefficients. So it's PV plus 2 raised to the first power times CL minus or minus 1 raised to the second power. And we don't have a K, we're trying to find KSP. So all we need to do basically is go ahead and take the molar solubility and come up with these molar concentrations at equilibrium, plug them in, and we get KSP. I added something to this. Let's see if it works. So in the problem, we said that the molar solubility, or the solubility at that temperature for lead 2 chloride was 0.0162 moles per liter. So what would then, if that's what's going to dissolve, what would the molar concentration of your lead plus 2 be? 0.0162 moles per liter. What would the molar concentration of your chloride ion be? 2 times that, exactly. 0.0324 moles per liter. So that's just from stoichiometry. You good with that? I was looking at this last night. I'm like, I think it should be, put little e's there. I don't know. I'm not always consistent. But the point is that at equilibrium, those are going to be the molar concentrations of your cation and your anion based upon that molar solubility. Then all we got to do is plug back into our equilibrium constant expression. And that's it. So our KSP, which is what we're trying to find, will be equal to 0.0162 raised to the first power times 0.0324 raised to the second power. Give ourselves 3 sig figs, and you're looking at a KSP of 1.70 times 10 raised to the negative 5th. So that's a classic, it's a classic sort of problem. Here in a minute, I can't remember where it's at soon or not, but the other problem is we're given the KSP and we're supposed to find the solubility. This one we're given the solubility and we're supposed to find the KSP. So what can you do with the KSP? Well, you can, and I said we're going to take the KSP and kind of backtrack it to the molar solubility. We can, and we're going to do some more of this on Monday, we can, with the KSP values of the salts involved, we can understand if a precipitate will form or not. And this is probably one of my favorite ones, is if you have like ion soup, we can, based upon the KSPs, understand which solid will form. Okay, which solid will form. Which solid will precipitate. So now I've just got some pictures for you. This is actually taken from OpenStax. And I don't know if you can see these on your slides. They're pretty little, aren't they? But they're also in OpenStax if you need them. Again, the smaller, like here we have barium phosphate. Good heavens. 6 times 10 to the negative 39. You know, you're like, so the whole product must be very low, so it favors the reactant, which is solid. So again, very relatively insoluble. Some more. There we go. Alphabetic. So let's do another problem where we have the KSP and we're supposed to knock out the molar solubility. Don't let problems like this throw you off. Molar solubility is kind of the thing we dealt with before. It's the moles per liter of, in this case, calcium carbonate that will dissolve. That's what molar solubility is. Kind of change it up this semester. I'm going with ice tables. So the initial change and at equilibrium. It's just so much easier to see what you got. So one of the first things I've been telling you to do is to take calcium carbonate, put an S next to it, put an equilibrium arrow, and show what it ionizes to form. So calcium carbonate solid is in equilibrium. We're talking about dissolving it with 1 calcium plus 2 cation and 1 carbonate, 2 minus ions. Write the KSP expression. KSP is equal to the molar concentration of Ca plus 2 raised to the first power times the molar concentration of CO3 carbonate minus 2, also raised to the first power, and we were given a value for KSP of 2.8 times 10 to the minus 9. So when I go to grading your Unit 3 exam, I'll kind of be looking for your work, something like that. So when in doubt, write the equilibrium. Why use an initial change and at equilibrium table? This will make more sense when we talk about something called the common ion effect. But if you just bear with me, this is the ice tables that we've been using before, where I'm going to have calcium, the molar concentration of calcium, the molar concentration of carbonate, initial change, and I'm going to put a line there and add the two and get my equilibrium concentrations. Now, it's all about stoichiometry. Not everything is, but this is again. Do you see where for every 1 particle of calcium carbonate, I get 1 particle of calcium plus 2 and 1 particle of carbonate? So that's where this plus X and plus X came from. That's from the stoichiometry. By golly, if I had a coefficient of 2 in front of either one of those, this would not just be X, it would be 2X. All right? So initially there was nothing, neither one of this cation or anion was present. It was just pure water. So that initial concentration is 0. Take 0 plus X, you get X. 0 plus X, you get X. That's it. Now, what we did before then was to take these equilibrium concentrations, plug them back into our equilibrium constant expression, and solve for the X. And that's all we're going to do. So in this case, what I've done, I see now I'm going to go slow, but what I've done is if we let X be equal to the moles per liter of the solid that will dissolve, then we have plus X of Ca plus 2 and plus X of CO3 2 minus. All right, so then it looks like this. When we substitute in, we get an X times X, which is X squared, is equal to the KSP, which was given. Now how can we get to X? Yep, take the square root, raise it to the half power. Exactly. That's it. X will be equal to the square root of 2.8 times 10 to the minus 9th. And that's the molar solubility. Give 2 sig figs. So 5.3 times 10 to the minus 5th moles per liter. On the previous slide, I really think to cover all your bases and for your own work to make sense, like I did on my slide, I would say let X be equal to the molar solubility. You got time on your test of the salts. Well, let's change it up a little bit. Things become a little more interesting when the stoichiometry changes, which it does for this one. We have another salt that is generally insoluble, silver chromate, and KSP is given. We're supposed to come up with the molar solubility. We should always write how the salt is going to ionize. So in this case, we're going to end up with 2 particles of your Ag plus and 1 particle of your CO42 minus. Once you write that, then you can write the KSP expression. And it would look like this. So KSP is equal to the molar concentration of your Ag plus raised to the 2nd power. And I'll tell on myself too, this is what gets me, right? Don't let it get you. Molar concentration of Ag plus 1 squared, because we have coefficient from the Ag plus is 2. Coefficient from the CrO42 minus is 1, okay, and our KSP was given as 1.1 times 10 minus 12. Now, we go ahead, again, state that let X be equal to the molar solubility or moles per liter of Ag2CrO4 that will dissolve. Then you end up with your ice table like this. Again, the initial molar concentration of your cation and anion is 0. But now, because of stoichiometry, you have molar concentration of your silver, your Ag plus is going to be 2x, and molar concentration of your CrO42 minus is simply X. At equilibrium, we take the initial, apply the change, take the initial, apply the change. So then the 2x and the x are going to be what's going to be substituted back into our KSP expression. So it looks like this. Again, don't let it catch you. This one, this first term, is representing the Ag plus. This one is representing the CrO42 minus. Notice that at equilibrium, I'm going to have 2x is my Ag plus, but I'm going to have to square that. At equilibrium, my chromate is X, and that's all equal to your KSP. The next thing that will catch us is we have to distribute that square through the quantity 2x. So we have to square the 2, and we have to square the x. So 2x becomes actually 4x squared. 4x squared times x is 4x cubed. Are we good with that? Let's see where that 4x cubed came from. So I don't think I show all the steps, but I think you're probably okay with it. I would divide both sides by 4 and then take the cube root of that quantity. Oh, I did show it. Divide both sides by 4. So quantity 1.1 times 10 negative 12 divided by 4. And then to get the cube root, if you take it raised to the 1/3 power, that'd do ya. So you're going to have to figure out how your calculator handles that. You do 1 over x or begin parentheses. There'll probably be a caret involved there somewhere. So giving us 2 sig figs, we got x is equal to 6.5 times 10 to the minus 5th, and that would be, by definition, moles per liter, molarity, moles per liter of the insoluble salt that would dissolve. All right. Any questions about that? And so you might see, well, there's a pattern, and there totally is a pattern, but you can't just use the pattern on the test. You have to show how it's developed. But there's definitely a pattern. So this, and I have a slide coming up to kind of summarize or say as much. This kind of shows you how, when you're talking about a particular, or a pair of salts, and you have their KSPs, and you have their molar solubilities, you can't compare KSPs and molar solubilities directly. So for instance, you guys would tell me this with the smaller KSP, that means it's less soluble, right? Smaller KSP, less soluble. The problem in comparing these two salts is that I have, like, if you want to say I have 2 particles here and I have 3 particles here. So that's why, even though this seems like it'd be less soluble, the molar solubility for this one is just a little bit higher. They're both to the 10 to the 5th moles per liter, but this is 6.5 instead of 5.3. So the molar solubility is a little bit higher, even though the KSP is smaller. And again, it has to do with kind of how you shake out. Now, I have this example where all of these salts form 2 particles, and yeah, you can look at their KSPs, and it directly relates to their molar solubilities. And so in this case, the one with the small KSP is going to be the least soluble compared to the one with the highest KSP, the most soluble. But that only works because we have the same number of particles. All right. Oh, here's what I said. Yeah, there is definitely a pattern. So if you are dealing with 2 particles, then as it turns out, your molar solubility is always going to be the square root of your KSP. Okay? And if you're working with something that dissolves into 3 particles, then your molar solubility is always going to be the cube root of the KSP over 4. So there's definitely a pattern, etc. So this is why we use, I think, an ice table, to work the problems that we've been working. The other reason to use an ice table is it's setting you up in a good way, not a bad way, for what we're going to be covering in Unit 4. It's called the common ion effect. And what this says is if you, I think of it as like you're seasoning a soup with a little extra this, a little extra that. Well, if you add a little extra this and it's part of a potentially insoluble salt, that salt's going to precipitate out. Okay. So for instance, here we have a clear beaker that has lead 2 cations and iodide anions minding their own business. And it's a soluble salt if you combine those 2. Or I shouldn't say that. I should say it's potentially insoluble. Now, probably a better way to say this. We have a tipping point. If we add too much, and we are going to add more I minuses, okay, in that dropper bottle is Ki, and here is Pb plus 2 and I minus. When we add Ki, potassium is going to be a spectator ion, but the extra little I minuses we add are going to force the lead 2 iodide to precipitate. It didn't precipitate here because it wasn't saturated. You go ahead and add more I minus, common ion, it falls out. Again, potassium is a spectator in all this. So let's do a problem and see what that looks like. So calcium carbonate, chalk, generally insoluble. Its molar solubility is 5.3 times 10 to minus 5th moles per liter. So what would its molar solubility be if we were not trying to dissolve it in pure water? What if we were trying to dissolve it in water that was already dosed with calcium nitrate? Now, nitrate's going to be a spectator. It's going to be your calcium here that's in your water. It's going to throw it over the edge. That's the common ion. Let's see what that looks like in how the numbers crunch. So calcium carbonate is our salt of interest. It's our insoluble salt. We should be able to write the balanced equilibrium. From the balanced equilibrium, we can write the KSP expression. Notice they're both raised to the first power. The KSP was given. So here's our ice table. Now, I told you, or for the last times we did it, we came up with the initial concentration of everything was 0 because we were trying to dissolve it in pure water. We're not dissolving it in pure water anymore. The problem says that it was running around with 0.1 molar calcium nitrate. So we have an initial molar concentration of calcium, and it's 0.10. Again, we're going to let X be equal to the molar solubility of calcium carbonate in this particular setting. So we can go ahead and do our X's. We're going to have the stoichiometry is a 1-to-1, so it's going to be plus X and plus X. Now at equilibrium, we do have a different sort of situation. I'm going to go ahead and draw my line here. At equilibrium, we have the initial and apply the change, initial and apply the change. So if you're already thinking, oh crap, okay, so this guy is going to go right here, and this guy is going to go right here. And you're going to end up with a polynomial. But wait, there's good news. So this is what we end up with. So we'll end up with what? 0.1x plus x squared is equal to 2.8 times 10 to the minus 9. And you guys have been doing those. And we can come up with about 2 solutions for x. But don't do that. Because actually for this sort of problem, I'm going to have you apply what's called a simplifying assumption. So one of your tasks in sorting out problems you're going to run into on the test is to recognize this sort of problem. If we assume x is, the double less than means significantly less than. This means significantly less than. Okay, so if we assume x is significantly less than 0.1, then our life becomes easy. Now, what is x? X is the molar solubility. X, by definition, is the amount of calcium carbonate that will dissolve. Well, you're dealing with an insoluble salt, so probably. See how that works? So if X is significantly small compared to the common ion that was already present, then this quantity, the 0.1 plus X, simply becomes 0.1, and your life just got a heck of a lot easier. It's called a simplifying assumption. To use it, you have to show, I think in my notes I probably say, I might say something like if X is significantly less than, double less than 0.10, and then I'll say then, then 0.10 plus X is equal to approximately 0.10. So can you kind of see what that's going to do? It's going to give you just x to the first power now. So let's go ahead and see what that changes. So this first term, 0.10 plus x becomes 0.10. We bring down our x, and then we also bring down our KSP. And at the end of this slide, I say always check your simplifying assumption. Okay, well, if this is the case, then, oh my goodness, x is just equal to 2.80 times 10 to the minus 9 divided by 0.1. I can almost do that in my head. Almost. I would use a calculator. So x in that case is 2.8 times 10 to the minus 8. And by definition, that was our molar solubility. Now, I hope this makes sense. The molar solubility in something that already has the calcium cation should be less than the molar solubility in pure water, because the calcium, the presence of that common ion kind of makes it so you can't dissolve as much. And they are. It is less. The other thing is, to me, I think our assumption was valid. We said, so in other words, is 2.8 times 10 to the minus 8, is that sufficiently smaller compared to 0.1? I'd say no. Okay, you can't even, if you take 0.1 plus this number, 0.10 plus this number, you're not going to see any change because you can only keep 2 decimals anyway. So yeah. All right. So always be sure to kind of check your simplifying assumption. Every once in a while, your simplifying assumption wasn't fair to say that was the case. On your test, you won't run into one of those. Okay, any questions? So that sets you up for doing A through, what did I say, J or something? Oh my gosh. You can do it.
So that answer was the molar solubility of the calcium carbonate.
Yeah,
That X equals 2.8
that was the molar solubility of calcium carbonate when the common ion is present in the amount of 0.1. Yep. Just talk too fast. Have a great weekend, though.